So imagine you had a couple friends that you wanted to shoot out of a cannon into space, all the way up into space. Let's say your first friend, you want to shoot not too far away, you just want to shoot them up a distance equal to the radius of the Earth. Your second friend, on the other hand, maybe you don't like them very much, you want to send them all the way off into infinity. What we want to do today is think about, if you're shooting them out of this cannon, what initial velocity you need to give to them in order for them to reach these two different distances. And what we're going to do is we're going to assume that there's no air resistance. We're also going to ignore the rotation of the Earth. And finally, we're going to ignore the gravitational pull of other objects, such as the moon. So this really will simplify things. For one, if we're assuming there's no air resistance, then we know that energy is going to be conserved. And in that case, we only have to think about the person's kinetic energy and their potential energy due to the gravitational pull of the Earth. So let's think about this a little better. So, both of your friends are starting at the surface of the Earth. So we know that their initial energy is going to be a sum of two components. It's going to be some initial potential energy plus some kinetic energy. And the kinetic energy, of course, is just going to be 1/2 mv squared, where v is this initial velocity you're shooting them out of the rocket with. And then finally, in both cases, they're going to have some final potential energy. But now we're going to assume that their velocity goes to 0. Your first friend, it goes to 0 when they're a height re above the Earth. And your other friend, the kinetic energy only goes to 0 when they get all the way to infinity. But either case, it's 0. So the way we're treating this is very similar to the way you would treat projectile motion problems in Physics 1. In that case, however, you are making an approximation. You were assuming that the object you were shooting was near the surface of the Earth the entire time, and so you could use the simplified formula mgh for their potential energy. In this case, however, we're sending your friends very far away, and then we need the more general formula. So the general formula for the potential energy due to gravity is given by negative g m over r, where in this case, one of these m's is going to be the mass of the Earth, and the other m is going to be the mass of your friend that you're shooting off. So as I said, we're going to treat energy as conserved because of the assumptions that we're making. And so that tells us that we know that the initial energy is going to be equal to the final energy. So now we can plug everything in. We can plug in u into u initial and u final, and we can plug in 1/2 mv squared for the kinetic energy, and that when we find is negative g, now the mass of your friend, times the mass of the Earth, divided by their initial position. So their initial position is at the radius of the Earth. They're standing right on Earth's surface, so they're a distance or radius of the Earth away from its center, plus 1/2 m, their initial velocity squared. And then finally, they're going to have potential energy gm, the mass of the Earth, times, I'll just write r final, since we have two cases that we're considering. And what we see is that the mass of your friends cancel out. So this is going to be something that's independent of the mass of whatever it is you're shooting up. And now we can solve for this initial velocity that you need to shoot up your friend with. And what we find is that the initial velocity is equal to g times the mass of the Earth, times we'll get a factor of 2. And then we'll have 1 over the radius of the Earth minus 1 over whatever their final position is. And I guess I'll write v squared. We could square root both sides. So now, in the case A, where the final position is given by twice the radius of the Earth, we can now solve for the initial velocity, and that's going to be given by the square root of now. So we'll plug in 2 times the radius of the Earth here, and with a little bit of work, we'll see that this is given by g, mass of the Earth, divided by the radius of the Earth, where the factors of 2 are going to cancel. And now if we plug in the values that I've given you here, plus g, big G, Newton's constant, what we find is that you need to shoot your first friend up with a velocity 7,910 meters per second, or approximately 17,700 miles per hour. So pretty fast. And then in the next case, B, where their final position is infinity, you're sending them all the way to infinity, never want them to come back. In this case, their final velocity is going to be given by, see, this term will cancel out. It'll go to 0 because we'll have 1 over infinity. So we'll have 2 g m e over r e, which now is equal to 1.2 times 10 to the 4 meters per second, or approximately 25,000 miles per hour. So of course your friend, who you want to go all the way to infinity, has to go a lot faster than your friend that only is going up to the radius of the Earth. Now this second case has a special name. This is called the escape velocity. And this is the velocity that you send anything away from, I guess you could consider it for other planets. This is the velocity at which you need to shoot something away such that they escape the gravitational pull of whatever you're shooting them away from. Thus the name, the escape velocity. So again, recapping what we did, we treated this problem in a very similar way to the way we treated projectile motion problems in the past. Energy was conserved. We were ignoring air resistance. And we just took this formula that we have for the potential energy due to gravity, and were able to find the initial velocity that we needed. So thanks.